This paper came out and it's called Mixture of Experts Meets Instruction Tuning, a winning combination for large language models, and it is by a whole bunch of people, uh, or a whole bunch of institutions. So you got Google, you got a bunch of universities here, so it's big, it's a lot of authors, so I guess a lot of work went into this. Now, what this does is it takes the Google FLAN model, which is it's a large language model, but they train it on a lot of data, and they have the scores here for how well it does. But it's a very good model, and if you combine that with Palm, then you have a really good combination. You have this really good large language model that's good at a ton of different tasks. And what they do in this paper is they say, well, what if we take that model, but instead of using a dense model, which is difficult to run, what if we use MOE, which allows you to parallelize operations, and it allows you to use less memory. And if you can get this MOE model working, this mixture of experts model working, then there could be potential memory savings upon inference time, which is very beneficial. So I haven't really seen any MOE papers that have done super well. I know that there's been a lot of MOE papers, but this is one of the first ones I've seen that does as well as they say it does. I am not sure if this is open sourced. I don't think it is at all, unfortunately. But even if it was, you probably no, you could probably run their models. But anyways, this is going to be a different read because it's more like this is what we did, and here are our results. And they kind of do different things to kind of get better results. So it'll be a different read than usual, but there still is going to be the technical aspect that I like to add with the MOE part. And because GPT-4, it was kind of leaked that GPT-4 uses an MOE type style in a different way from what this paper is doing, but maybe GPT-4 does it in this way as well. Anyways, yeah, let's get into what they do. So the first thing is, what is MOE? So MOE is, if I have, say I have model 1, and then I have model 2, and this is just going to be abstracted. Say I have this like data here. So I have some data, and then I have model 1 and model 2, or expert 1. I'll call these experts instead. Expert 1 and expert 2. Then what you can do is you can take, say, like a part of this data, say this half of the data, put it through expert 1, and this half of the data and put it through expert 2. Or maybe you put all the data through each of the experts. And then you can combine them in the output to get your data again, but your transformed data. But each of the experts, so expert 1 and expert 2, since they're different models or different, the weights are not shared, then they're going to come up with different strategies, hopefully, to look at this data. In a way, multi-head attention is kind of doing something like that, but it's at a very small scale, so it's not a mixture of experts. But yeah, you could also take the whole data and put it through each of the experts, and then maybe this expert finds out something about the data, and the expert 2 finds out something else, and then you combine it using some average, and this may be better than just sending this through one model altogether. And let's say, normally what you would have is you would have data, you would pass it through the model, and then the model would output your transformed data. But let's say that expert 1 and expert 2 have the same amount of parameters as model 1. If you put expert 1 on, say, GPU 1, so this would be on GPU 1, this expert 2 is on GPU 2, then you can get twice as much, you do twice as much compute in parallel. So if you throw the data on expert 1 and on expert 2 at the same time, and it takes the same amount of time, but you could get there could be more representation power because you're using two experts instead of using one model that has to do everything. So specifically in large language models, the way MOE works is so you have this token sequence here. So we have our token sequence that's of shape S by E. That looks something like this, and I have a diagram here. But yeah, you have this token sequence here. And for each of the tokens, so I'm just going to take this first token here. Sure, I can use purple. I take this first token here, like that. And we're just going to look at one token for now. What you do is, well, there's two ways to do this, but you send this through a router. So you send this through a router, and the router basically says which network do I want to send this data through. And each of these experts, so this will be feed forward 1, feed forward 2, and feed forward 3. So we'll say we have 3 experts. And before I do that, I'll give you context for. Yeah, I'll just leave it at that. So we have 3 experts, and we're taking one of these tokens. This token may represent the word, say, maybe it represents the word I. Then this router will send this data through a selected number of experts. Let's say we have k is equal to 2 experts that we send this data through. Then this may send the data through feed forward 1 and feed forward 2. And then you collect the data. So you'll collect this data, and you'll combine it together using some weighted average, or maybe you add them together, or maybe you multiply them together. And then you have your output, which is the same shape. And this is your new token, your new representation. So that's a high level of how this MOE works. And you do this for each of the tokens. But at a more low level, if we have a token here, so there's 3 parts to it. And so the first part is you take you take your token, and put through you put it through the gate. So our gating function could be, say, G is equal to softmax of W sub G. So that's our gating function multiplied, or dot product, by the I guess it would be x dot G. X dot WG. So you just multiply x, which is our token here, and you multiply that by the weight matrix, and your weight matrix is going to be of shape, this will be E, and then it'll be the number of experts. So whenever you multiply x by W, you're going to get this vector out that is of shape number of experts. So in this case, it would be 3. In our example above, this would be a vector with 3 values in it. And it'll be a softmax distribution. So say it looks something like that. And this value may be, say, 0.7, 0.2, and 0.1. And we take the top k values and we send the data through there. So the second part, so now that we have our softmax function, then we know we're sending it through, I guess I used 1 indexed above, but we know we send it through expert 0 and expert 1. We do not send it through expert 2 because we're using top k, and k is equal to 2. So now what we do is we route the info, and we route the info, and then we do the operation. So we know that we want to send our vector x to expert 1 and expert 2. So we have our vector x, which is of shape E, and we send this through feed forward 1 and feed forward 2. Expert 1 and expert 2, I'm not going to 0 index these, 1, 2, 3. And we do not send it through expert 3. Now, each of these will output a vector of shape E as well. That's what you usually do in after your attention mechanism. So this would be x1, x2. So now we have two copies of this original vector x, and now we need to combine them. So step 3 is combine. And the way we combine them is by using the probabilities that we had up here. So in this case, we had 0.7 for expert 1 and 0.2 for expert 2. So to combine these, we would have y is equal to, let's say the first item is g sub 1, and the second item is x, so our first vector is x1, and then we add this to g sub 2 and x sub 2. So it's a weighted average according to the softmax probabilities that were outputted. And you can see that this is differentiable because we're multiplying the probabilities, which we got here, the probabilities here, by the function itself. And if we differentiate with respect to y, then we also differentiate the gating function, which means that this whole process is differentiable, and our weight matrix here gets our w sub g, that gets updated. And if you do this some other way, you may, like the difficult part of this is making this all differentiable, because this selection strategy is, it's kind of unintuitive how to make that differentiable, but this does it if you do the weighted average, and that's usually what's done. Now you usually put these at the right after the attention mechanism. So if you've seen so normal self-attention, if you've seen how that works, then you usually have, say, your layer norm. So you throw it through the layer norm, or I guess this would be attention. So you throw it through the attention mechanism, your input vector, or I guess set of input vectors, but it broadcasts to the whole sequence. And there. And then you send this through your layer norm, and you add the residual connection. And then you usually send this through your feed-forward network, and then you get your output. But instead of sending it through a feed-forward network, you're going to send it through this module here, the mixture of experts model. So you get your output, say, x hat, and this is going to go through your mixture of experts. So your feed-forward 1, feed-forward 2, feed-forward 3, and it would go through 1 and 2, and so on. So this is your mixture of experts model that we showed above, and then it would output a new vector, which would be, say, x bar. And then you send this through layer norm, and you add the residual. So all you're doing is you're replacing the feed-forward network module after the attention mechanism with a mixture of experts model. Now there's a second way of doing this, which they bring up, and to notice how the tokens, so our token got multiplied by a weight matrix, token multiplied by a weight matrix, and that kind of gives you, you can kind of think about this as token X saying, I want to go to the first expert. So token X is saying, I want to go to the first expert and I want to go to the second expert. Now, another way of doing this is having the experts choose which things get to go to them. So the way you can do that is we have our sequence here. So we have our sequence, this is x1, this is x2, and so on to xn, or x sub s. And you have, say, expert 1, and you have expert 2. Now what you can do is you can multiply the whole sequence by that. So you multiply the whole sequence by a weight matrix, and you have each of the experts come up with a probability distribution. So expert 1, let's say the distribution is in black, then it would look something maybe like this, like that. And then if we're routing the top k is equal to 2 vectors, then you would route this vector to expert 1 and this vector to expert 1. And then if we have expert 2, which I will draw in red, expert 2, and they have a distribution that looks something like this, then it would take, say, token 2, and then I guess I can make this a little different. and it would take token S. So then it does the operations on those tokens, and then it'll output the new tokens. This would be x hat 1, and it'll also output x hat 2. And then your expert 2 would output, say, x bar 2 and x bar S. No, this was x bar S. This was not 2. This was, yeah, this would have been S here. That would be S. And then you combine these like normal, using your distributions down here, just like you did with the other mixture of experts up here. So that makes it still differentiable, but instead of each token choosing, you can kind of see that each expert is choosing. So these are the two ways you can do mixture of experts. Now, that's the main like technical piece of this model. The rest is just how they train it. So the other thing I want to go over is what exactly is instruction fine-tuning. And they have a perfect description down here, or up here. I think. Yeah. One particularly successful paradigm. Let me get out my highlighter. One particularly successful paradigm for training such models is instruction tuning, which enhances their performance on specific tasks by adapting their pre-trained representation to follow natural language instructions. So if you've seen like Instruct GPT, which is what the back end of ChatGPT would be using, you basically train this thing, or you so you train this large language model. So you have a large language model, and you have this massive data set, and this data set D is just a bunch of text. This is just internet text, and you train your model on the internet text. Now you have this pre-trained model. So you have this pre-trained model, and what you do is you take this smaller data set, which is a little bit smaller, and you fine-tune it on that, but this is your instruction data set. So this may be something like, I want you to add 1 and 2. And then the output would be 3, obviously. But it may be something like the output is 3 or something like that. And you do your instruction fine-tuning on this model so that it, like if you just train on text, then it'll just try to complete your text. But if you fine-tune it on instruction fine-tuning, it gets a better idea of what you're looking for, and it kind of gets it in a mood to work with humans. If you just train it on text, then it'll take your text and it may respond, or it may just complete your text because it's only trained on text completion. So the idea is that just training on instruction fine-tuning, that is really good, but you can make your model even better if you do instruction fine-tuning, or if you do instruction fine-tuning on a mixture of experts model, where your instruction fine-tuning has a ton of data in it. So if we go to the training data, we can see that there are a ton of tasks, 1,836 fine-tuning tasks. And intuitively, you can think of each expert as kind of dealing with one of these tasks. In your mind, you can kind of think of that, think of it working that way. And they show later that each expert kind of does that, where each expert kind of specializes in something. One expert may specialize in dealing with, say, data about addition, while another expert may deal with data about just responding to somebody in a thoughtful manner, something like that. So you can see they have this massive training data set here, and the way they evaluate it is they do few shot and zero shot, where they just hold out a little bit of this data. We'll get to this table at the end. Now, we'll just go through this line, or kind of paragraph by paragraph, but the first thing is the dense model size. So that is up here. And you can see that the first thing they show, which is according to these results, which we'll look at the end, is So you can see that the circle is the basic flan model, and you'll see MOE everywhere, and that is the mixture of experts model, which is the triangle. And you can see the G flops per token prediction as that goes up, as the number of flops needed to do prediction, which basically means that the model size increases. You can see that obviously the accuracy goes up, but for every task in general, you can see that the MOE model outperforms the base T5 model, even though they have the same exact compute, or the same number of flops, and you can see that they have that in this task as well. What tasks are these? Some tasks, whatever those are. Now the expert number. So the expert number is an interesting thing to look at. If you may think that, oh, as I increase the number of experts, the model will do better. So they say that this is an easier task, MMLU, and you can see as you increase the number of experts. So what is the blue one? It's probably a smaller model, but as you increase the number of experts, I think that's a smaller model, it'll do better. But it kind of flattens out, and you can see in this other model, which is also an MOE model, because this is I think this is just a larger MOE model. You can see the performance actually decreases, and there may be too many experts to route to, and the model may get confused and it doesn't know how to route information properly, and it may have issues trying to just remove experts it doesn't need. So you can see 120 experts, and if you have 120 experts, then they may each want to specialize in something else. And if they each specialize in something else, then you're probably going to have useless experts there just doing nothing and getting in the way of performance. So there is a point at which the number of experts doesn't become that helpful. Now, with a more difficult task that they say this is more difficult, you can see that the scaling properties do kind of hold, where as you increase the number of experts, the score increases. I don't know how much this holds because they just have 3 different experiments, 3 different types of models, but you can see that sometimes it does better, sometimes it doesn't do better. Now, we'll get to this part later. So those are the first 2 things. You can see that the MOE generally does better than the normal dense model. So if you just add MOE instead of using the feed-forward network, then it generally does better. And the expert number, as you increase that, it does better up to a point. Now the routing strategy. So this is interesting, and this is where this strategy comes in. So you have a top 1 token choice gating, which is what flan switch did. So that would be k is equal to 1. And that would be this first method here, where you just have you multiply each token by a weight matrix, and you get a softmax distribution over all the experts, and the token chooses the experts. G-shard top 2 token prediction, or top 2 token choice gating, that is represented by flan GS. This is k is equal to 2, and it's just k is equal to 2 where the token chooses, so it's just this here where k is equal to 2. So you have k is equal to 1 where the token chooses, and k is equal to 2 where the token chooses, and that's represented by GS. Now you have top 2 gating flan EC model, and the flan EC model is I think this is the one where the expert here, where the experts choose the tokens at once. And it uses top 2. So 2 tokens go to each expert. So each expert gets to look at all the every single token, and it chooses 2, basically. And if we look down here at this, then you can see that the triangle, which is the EC model, so the EC model was the one where the experts get to choose, you can see that generally does better. So if we look at the bottom part here, I'm going to reduce my highlighter size. So if not 100, if we look at the bottom one here, then you can see that just increasing k to 2, so that'll go from the square to the hexagon, increasing k by just 1 to k is equal to 2, does better overall. And then increasing, or having the experts choose 2 tokens instead of having the token choose 2 experts does better as well. And this is the easy task. And in the hard task, you can see it does even better. And there's even more of a performance gap between experts choosing versus having the tokens choose themselves. So that's also an interesting result. And from now on, they have the experts choose. So fine-tuning strategy. Now, remember, we had to fine-tune this model, and since we have this mixture of experts model, then one of the problems is, this uniform routing problem. So if you have, say, 3 experts, where are my experts? Yeah, if you have 3 experts, and let's say we have 2 tokens, then, say we have 3 tokens, then what you may have is, say, this first token really wants to go to the first expert, and the second token really wants to go to the first expert, and let's say the third token also really wants to go to the first expert. So they all want to go to the first expert, and if we let k is equal to 1, then they'll all go to the first expert, and expert 2 and expert 3 are basically useless. They're not used at all, and since all the experts just want to go to the first since all the tokens just want to go to the first expert, then you basically have all this other compute power that you're just not utilizing at all. So they have an extra loss term here, where alpha is some control parameter, and this is just an average. I think that should actually be 1 over e, not e, 1 over e. So this is just an average over 2 values being multiplied together, so fi and pi. So fi is the fraction of tokens routed to expert I. So in this case, for the first one, it would be 3 out of 3 times whatever the probability is. That's the average. It's the sum of probabilities. So let's just say it's 0.7. So you all really want to go to expert 1, and then you have 0 and 0. So it'll be that plus 0 plus 0. Now to minimize this, you would have it kind of average out over the whole over everything here. So whenever you're minimizing this, the fraction would kind of average out so that each expert has to be utilized. And if it's not utilized, then this loss term will be a lot higher. So this is the first thing they add. And if you just have the normal experts here, then all the tokens will probably go to 1 expert. But if you add this loss here, then it'll encourage the tokens to choose different experts as opposed to all tokens going to the same thing. And yeah, that's pretty important to do. I think they show here. Yeah, they show here. Actually, before we get to that, one other thing is, so whenever you're doing these mixture of experts models, there's a lot of different things you have to do to try to get them to work. So there's also freezing strategies, where I could freeze an expert. I could say freeze expert 1, so then that may convince the tokens to move to expert 2 and expert 3. Because the expert isn't really doing anything, it's static, it's not changing, it can't be updated. Or perhaps I could freeze the routing function. So if I freeze the routing function, then everything gets moved, then the tokens while you're fine-tuning it will get moved to the experts, but the way the tokens get moved doesn't change, only the experts change while you're fine-tuning. So they have these other strategies. And if we look at the table here, you can see that only 2 of the strategies work. So if we look here, we have our baseline and we have our gating function. So you can freeze the gating function, you can freeze an expert, or you can freeze MOE in general. Now, if we look, we can see that in general, freezing the gate actually does better. So if you freeze the routing function, it does a little bit better than if you don't freeze anything. Interestingly, I don't know why, and I think they say that there's like a minimal gain there. So that's something interesting. I don't know why that happens, but they say it does. And then the second thing is they have this z-loss function, which is an alternative to this basic this uniform loss function. But if you use the uniform loss, it increases. So using the uniform loss, so that so all the experts are utilized, that increases the scores. While using this z-loss, I don't know what that is. It's some other loss metric that does not. So freezing the gate and balancing the experts help. Now, fine-tuning versus instruction fine-tuning. So this is kind of interesting. So yeah, we'll just read through this. So for the examined held out tasks, we observed that the improvement of MOE over fine-tuning MOE is larger to the performance between flan T5 and T5. So I think what this is saying is that if you're directly fine-tuning the MOE, so yeah, I think they're saying if you fine-tune MOE, that's better. Like you get a better gain than if you just do normal fine-tuning. I think that's what that's saying there. And then MOE architectures are prone to overfitting during the fine-tuning process. So that's one of the biggest problems with MOE. Since you have all these experts, there's a lot of, and you route to them. Each expert has a lot of power. It has a lot of expressive power that it can add to the that I can add. And since you're adding this expressive power, each expert can overfit to the specialized task that it's doing. And maybe that explains this right here. If you freeze the gate, maybe that keeps the experts from overfitting. But yeah, that's one of the things they say here. And where a single task fine-tuned MOE model sometimes underperforms their dense T5 counterparts. So that's one of the problems with MOE that they bring up here. And then they say, in general, MOE model performance scales better with respect to the number of tasks other than the number of experts. So scaling the number of tasks is better than scaling the number of experts in general. And these are some of the conclusions they make when doing this instruction fine-tuning. Now, expert specialization. This is what I kind of talked about at the beginning, where as the model size increases, the expert specialization kind of occurs. And that's what you would expect. In general, you would expect that as you increase the model size, each expert can leverage its specialized task in some way. If your model is too small and you have experts specializing in something, the model may not be able to use that specialized addition that expert adds. So you need to have model size to use this mixture of experts, which is unfortunate. And I think that's why we haven't really been seeing mixture of experts do that well in general. And you also need to train this thing right, because if you, like we showed right here, you need to have gating and you need to have this balance loss. And there's a lot of different aspects here that go into training this mixture of experts model. Yeah, and then the final thing they show here, that the expert usage goes up as the model size increases. And then the final thing that I found interesting in this paper is the fine-grained specialization of the MOE models is that they do not do that good on multilingual tasks, which is very, very weird, I found. And you wouldn't expect that because each expert may be able to specialize in its own language, but maybe each expert doesn't have enough specialization power to do that. But I found that interesting. Yeah, anyways, that is pretty much the paper where they say if you just use MOE, that's better than just using a normal model in general. And we can see the results here. Hopefully my tablet renders this well. I'm going to move this over, so hopefully it does. So if we look at Palm or Flan Palm, and we look at Flan ST, where ST is the best model they use, that is using the expert choice, and then that's using all the other things they had below where you freeze the gate and stuff like that. If we throw everything at this, then you can see that the massive model here, this is the 64, yeah. The massive model, no, not this model here. Yeah, this is the model they look at. So not this model, but this model here. If we look at this model and we look at the model all the way down here, so these two, and let's compare their scores. So first you'll notice that this model size, the original Flan, the Flan Palm model, and the new model size, this model is much larger, the mixture of experts model. But if you look, the flops per token is a third of the size than the Palm model. So even though the mixture of experts model has more parameters, the compute power, or the number of flops isn't as much, and that's because each expert can be distributed. And whenever you're doing, the benefit of using MOE models is this exact thing. You can have a lot more parameters, and it doesn't use nearly as much compute as a non-sparse method. So as this method, so the Flan Palm model is not sparse, and you can see it uses 3 times as much flops as the Flan ST model, the MOE model. MOE. Now, if we look at the scores, you can see MOE wins here, MOE wins here, MOE wins here, 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 and not on this one. But in general, out of, what is this, 1, 2, 3, 4, out of 5 tasks, MOE beats the full model. So maybe if you increase the mixture of experts model by 3 more so that the compute matches, maybe it'll probably do even better than what we have here. But you can see it pretty much outperforms the model, which is of the same compute power relatively, by quite a good amount in most of the cases, except for this case. This is QA direct. So I guess a mixture of experts sucks at answering questions, but yeah, that is the whole point of this paper. That's saying if you have MOE, or if you just have instruction fine-tuning, which is this, Flan Palm, so if you just have this, and if you just have Flan, or if you just have Palm, and you fine-tune using Flan, then you get something that is really good. But if you instead have a mixture of experts model and you fine-tune a Flan, then you get something that is even better than if you just did instruction fine-tuning. So instruction fine-tuning plus MOE is better than just instruction fine-tuning. Also, if you just have MOE, then that's not as good as the base model with instruction fine-tuning. So you need to have both. You need both MOE and instruction fine-tuning, and that's what this paper says. It's saying you need both of these to do well, and it shows that it does pretty well in almost all the cases. So overall, pretty cool paper, and kind of shows how MOE works in general. Yeah, it's a different read than usual, but yeah, I think it was an interesting paper.